Okay, class, welcome to today's lesson. Today we're looking at interpreting and sketching graphs. Our big focus for interpreting graphs are going to be two things. Number one, it will be the title of the graph, as in what's being graphed, and the second thing will be your axis titles. Because those things are going to be very descriptive, and they're going to help us tell what was graphed. And the last thing we're going to look at will be your slope. Your slope also communicates what's being graphed, because your slope is called your rate of change. So when we're looking at just a line like we've been looking at, we just refer to it as slope. But when we have science type graphs like these guys, then we refer to it as the rate of change. And it's not a rat, it is a rate. So let me fix that up. Rate of change. So your rate of change tells you how fast, slow things are changing. It also tells you if the rate of change is increasing or decreasing, or if it's constant. So your rate of change is very important. If your rate of change is constant, then what happens is you have a straight line. And that's what we've been looking at. So far we've been looking at straight lines, and that's because we have a constant rate of change, ROC. So rate of change was often abbreviated ROC, and if it's a constant rate of change, then it is a straight line. Straight GHT line. Okay, if it's curved, it can be one of two things. So if it's a curved line, then guess what? You have either an increasing rate of change or you have a decreasing rate of change. It all depends on how it's curved. So for an increasing rate of change, what you would be looking at is you'd be looking at your rate of change going up like that. So it'd be curving up. Okay, so starting off small and then increasing. If you have a decreasing rate of change, so things are slowing down, then what happens is you have the rate of change curving down. Okay, if you have a constant rate of change, which is what we have been looking at, then what you simply have a straight line. Just like that, super straight. So your rate of change is really important. It helps us tell what's going on with our story, interpreting the graph. For your slope can, or your rate of change can be many different things. So for example, for your rate of change, if you have a rate of change and it's monies per hour, that is what we call a wage. So your wage is actually a rate of change. Okay, it's the change of your pay as time passes. Another very common rate of change is how you got to school today, probably in a car, and so it's going to be kilometers per hour. And what do we call that? That would be speed. So those are two common rates of change. Okay, speed and wages. And those are ones to use all the time. So now we're going to have some fun. We have a constant rate of change, we have a decreasing rate of change, we have a rate of change that increases, then decreases, and vice versa. Decreases, then increases. So which one is which? Looking at the scenarios here, we have to match it for the graph. So let's see here, temperature of a cup of hot tea over time. Well, what's going to happen with that temperature? Number one, it will decrease right away. Okay, so you're going to see the temperature go from high to low. So we're not talking so much about the rate of change, but we're talking about the actual temperature. The actual temperature will start high and then it'll start low. So right away, it's not graph A because that starts low. And it's not graph C because that starts low. So process of elimination, it's one of those two. So if you boil a cup of water and you let it sit, the temperature would go down, that's correct, but then would the temperature go back up? No. But graph B is correct because you start up high and the temperature goes down, and then once it gets to room temperature, it's going to start slowing down. And it'll just adjust to room temperature and not cool down any further. So that's what happens with the temperature of a cup of hot tea over time. There will be a decrease in the rate of change. So this is B. Next, speed of a bike over time is the rider bikes up and down a steep hill. So as you bike up, what would happen to your speed? Well, your speed would slow or decrease. And then when you bike down a hill, what happens? Well, you start off slowly, but then your speed will increase. Whoops. Increase. So this one here, it's going to be graph D. Your speed will go down, and then your speed will go up. Okay, so this is going to be D. Next one, a car accelerating at a constant speed. Constant speed is the key phrase there, so that's going to be definitely A because it's got to be a straight line. Okay, so it'd be meters per second, not kilometers. Well, it would be kilometers per second, but meters per second for the start, and then you would go up to kilometers per second if it's long. The height of the football, so looking at the height of a football as it's kicked across the field, height's going to go up and then it's going to go down. So the height increases, slows down, and then it decreases. So this is going to be graph C. Okay? So matching the graph to the situation takes a little bit of tricks, thinking through, and some tricks. So the first trick is you got to label the independent and the dependent variables. The dependent variables, the one that's the most common is independent variables, rather, is time. Okay, so time almost always is independent. And dependent is what you are going to measure. What you can do to help you is a depends on sentence. Okay, so what we do is we have something depends on something. And so you're going to use what we're graphing and fill in the blanks for that. This one here would be your dependent because it depends on. So when you're doing your depends on statement, your dependent belongs there. And the next one, this one over here, would be your independent statement. Independent. E-N-T. I always spelled dependent wrong. It's one of those things. Sorry. So, for example here, now here's a trick. One sounds kind of correct, but then the other one sounds very correct. So you got to try it both ways. So, for example here with number one, we can say temperature depends on time, or should we say time depends on temperature? So which one sounds kind of correct and which one sounds very correct? Well, this one doesn't really sound that good because whatever the temperature of the tea is, it's not going to change the clock. The clock just runs. But how long the hot water's been sitting does change the temperature. So the temperature depends on the time. Okay, so then what you can do is label your graph. Over here for graph B, okay, time will be independent and the temperature will be dependent. And almost always temperature is dependent because you're measuring it with a thermometer. Next one, speed of the bike. So does speed of the bike depend on time, or does time depend on the speed of the bike? Well, time doesn't depend on the speed of the bike. The speed of the bike depends on time. So for graph D, time, again, is almost always 99.9% down there, and the speed of the bike will be right here. Okay, So this will be your independent, and this will be your dependent. Remember where they go. Okay, independence. OMG, my bad. Dependent. Let me just graph this properly. I am so sorry here. This will be independent. And this one here is your dependent. Okay. Good. Going over here for the next one here, a car accelerating at constant speed. Okay, so a car accelerating at constant speed, that's going to be kilometers or distance. Distance over time. Okay, and that's a tough one because you have to figure out what acceleration is. Okay, and here, let's use this as km, not meters per second. We'll assume the car starts going very fast. Height of the football as it's kicked across the field. Okay, so we have time as your independent, and we're measuring the height. Your height is your dependent. Okay, so the height depends on time, the speed depends on time, the temperature depends on time, the distance depends on time. There we go. So when comparing two quantities, straight lines, they indicate a constant rate of change. The steepness of the line indicates the rate at which one quantity is changing in relation to another. Curves are used when the rate of change is not constant. Okay, and the last one is a horizontal line means no rate of change. Things are still happening, but there's no change occurring in the height or the speed or the temperature or the distance. Okay, so let's have a look at this graph right over here. Okay, so a horizontal line would be something like this, completely flat. Okay, good. Looking over here, we're going to read this graph. So things that you want to look at, its height, its time, and the description right here. Okay, it shows the height in meters of a small radio-controlled plane as a function of time. So this would be an airplane. Airplane's height over time. Airplane's height over time. Okay, or over airplane's height on a flight. I like that better. I don't like using the axes in the description of the title. Not that it's wrong, it's just better if you don't. How long was the plane in the air? So basically, you start at 0 and it went for 15 minutes. So it was in for 15 minutes. That's how long it was in the air. Next, what was the plane's maximum height? So we're going to look here. Here's our height. The tallest height was here. Now this is a 5. So we have 1, 2, 3, 4, 5. And we should have meters. Okay, there should be the unit meters. This person, I think it got blocked off by the graph. So this would be the maximum plane's height of 6 meters. Next, what was the total vertical distance? So vertical distance is up and down, covered by the plane during its flight. Well, let's have a look. So from A to B, what happened? Well, it went up 6 meters. From B to C, what happened? It didn't go up or down. It just flew at the constant height. So it flew steady at a steady height. Then from C to D, well, here it went down 2 meters. Then from D to E, it went up 2 meters. And then from E to the ground, it went down 1, 2, 3, 4, 5, 6 meters. So altogether, it traveled 6 plus 2 plus 2 plus 6. It doesn't matter that it went down. We won't treat that as a negative number because it just wants to know the distance covered, okay? And so altogether then that would be 12 plus 4, 16 meters up and down that the plane changed vertical distance. So let's begin a little journey to explain the different sections of the graph. From A to B, what happened? Well, we're going to say that the plane rose 6 meters over 3 minutes at a constant rate of change. Because the lines are straight, we got to mention the rate of change was constant. So I'm kind of talking about the time from here to here would be 3 minutes. And I'm also talking about the vertical change as well. So the plane rose, or you can use different words. The plane increased its height, or the plane went up, whatever you want. I'm going to say plane went up 6 meters over 3 minutes at a constant rate of change. At, a constant rate of change. Okay, so I'm mentioning what happened and just kind of describing it for each segment of the graph. What about B to C? From B to C, it doesn't go up or down. It's still flying, but it's flying at a constant height, at the same height. So I'm going to say here there is no change in height from B to C. Sorry, no change in height for 2 minutes. And what we say there is no rate of change. Because there was no change. Okay. Then we'll go from C to D. Well, from this section on the graph, from C to D, it went from 5 to 9 minutes. So that's a total of 4 minutes. And it went down 2. So I want to describe that the height changed by a decrease. So I can say the plane decreased in height, or the plane descended. Okay, so it's good when you use words like descended or ascended. Okay, or increased or decreased. Right? Those are other good, valuable words to use when you're describing a graph. Increased, decreased. I do have those the other way around. Maybe I will switch that. Decreased / increased. Okay, so for CD, plane descended 2 meters during 4 minutes. Okay, and it's a straight line, so you would say at a constant rate of change. Okay, done. Then what about DE? What happened at DE? So DE right here, between those 2 points, that occurred for 1, 2, 3, 4 minutes, and you went up how much? 2. Okay, so you went up 2. And it's a straight line, so it's a constant rate of change. So for DE, you will say the plane ascended 2 meters over 4 minutes at a constant rate of change. There you go. And what happened to E and F? Well, the plane went down, and what happened at the end? It landed because the height is 0. And that happened over 1-2 minutes. So it happened pretty quickly, didn't it? And it went down 6 meters altogether. So that's what we're going to say. The plane descended 6 meters. Plane decreased the height, or descended, your choice. Decreased height of 6 meters in 2 minutes at a constant rate of change. And what else can we add? Well, we can add that the plane landed. Okay, and so we can then say plane has landed. Oops. Plane has landed. There you go. And so that's describing each section of the graph. Just kind of saying what each variable is doing. So I'm looking at my dependent and my independent, and just describing what happened in that section. Okay, next page. So we're not going to do too much graphing, but I'm going to kind of demonstrate this very quickly because the bottom is what's really important. So the first thing is we have to decide which one is dependent versus independent. So we're going to do a depends on sentence. Depends on sentence. So we have study of bee pollination. He collected data on the number of bees present in a honeycomb every 2 hours during the day. Okay, so it's going to be Josh's data will be time and the number of bees. So we have to figure this out. We have the word time and we have number of bees. Which one's dependent and which one's independent? Well, let's see here. Let's take this one, put it here. And it says time depends on the number of bees. Nope. Time does not depend on anything. So that is not correct. So let's flip it around then and try that one. Whoops, I missed part of it. I'm not sure how that happened. There we go. So move time over here. Number of bees goes there. And so does the number of bees depend on time? Yeah, it does. Okay, the number of bees depends on the time of day. And so what we can know then for Josh's data, okay, this is going to be our independent. It'll be our X values, and it will be our domain, and it'll be our inputs. Okay, and this here number of bees, that will be our dependent data. It'll be our Y values or our range. And what else? It will be our outputs. So a whole bunch of different words to describe each one. Next it says graph the data for both should you join the points. We'll talk about that later. What about Kyla's data? Time and temperature. So blank depends on blank. Do a depends on sentence. Which one is dependent, which one's independent? Does time depend on temperature? Not really. It makes more sense to say that the temperature depends on time. So the temperature of the depends on the time of day. Okay, so this here would be your X values. This would be your Y values. Next, graph the data for both should you join the points. Well, that kind of depends on down below. Okay, so we have two types of data, discrete data and continuous data. What is discrete data? Well, discrete data's values on a graph that are whole numbers. So with whole numbers, guess what? It doesn't make sense to have values in between, all right? There are no values in between. So it does not make sense to connect the dots. Because when you connect the dots, you're saying there's values in between them, but there isn't. Okay. Now the exception would be, there's one little exception, is if you were graphing large numbers. The exception is when you have very large numbers like thousands or hundreds. Because if you're graphing hundreds of bees, in between, say, 100 and 200, there's a lot of numbers, isn't there? 101, 102, 103. So in that case, you would probably connect the points because there are some values in between since the numbers are so large. So if you have large numbers, it's still discrete data, still discrete. Bees are whole numbers, so you don't have half a bee flying around, but you have large numbers, so you do connect the dots. Okay, so if you have large numbers, then you can connect the dots. Whereas that's different with data values that are continuous. So continuous data values, they are easily broken into smaller values. Oops, broken into smaller values. Like temperature, right? In between 1 degree Celsius and 2 degrees Celsius, there's a lot of decimals. Money, in between $5 and $10, there's a lot of decimals. Volume, right? Looking at decimals. So there's lots and lots of things that have continuous data where you would actually connect the dots with a line. Okay? And with smaller values, you're looking at things like decimals and fractions. Right? So if it makes sense to write them as a decimal or fraction, then you're going to have continuous data. So the example for this one is temperature, money, time, volume, mass, distance. Okay, so what are some examples of discrete data? Well, whole numbers. For example, people. People are whole numbers. Houses. Houses are whole numbers. Animals are whole numbers. Okay, you don't see half a dog walking around. Here's a good one. Jugs of milk. Right? When you're going to the store, you got to buy the whole jug. You can't dump out half and then say, hey, I'm only paying for half. That won't go well for you. Okay? So people, houses, animals, jugs of milk, things that are going to be whole numbers. Good. So again, graph of discrete data can only show points, only points, right? Because the values in between them have no meaning. All right? So let's have a look here. This will be Josh's graph. So Josh, since he's got bees, he will have discrete data. So should you join the points? Nope. It will be points only because B/C because discrete data. But you look at Kyla's data, hers is temperature. So should you join the points? Yeah, absolutely. Because it makes sense for temperature to have values in between. So Kayla, oops. Hers will be continuous. continuous data, so you will definitely want to join the points. Man, it's long. Okay. Good. So looking at graphing this then, here we'll put Josh's data. This here will be the number of bees. And this will be time in hours. Always have your units in brackets. So let's go make a grid real quick. Okay, so then we have to decide on what we should do for the number of squares. So when we count, let's count the number of squares we have. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 17 squares, okay? So for Josh's data, we had 17 squares. Oops. And we have to look at the number of bees. The largest number is 26. So it would be 26 bees divided by the number of squares. That's going to equal how many bees should be in each square in order to make this work. So when we divide, we get 1.52. So that would be 1.52 bees per square. But it doesn't make sense to graph that. What you want to do now is you want to round up. Okay, round up to a nice number to graph. And so what we're going to do is we're going to graph each square represents 2 bees. Okay, so 2 bees per square. So we can then start here at 0, and we can go 2, 4, 6, 8. This will be 10. Notice I don't have to write a number on each line. 12, 14, 16, 18. This will be 20, 22, 24, 26, 28, 30. Okay, and then we can do the same thing for time. So count the squares. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So here we had 19 squares. So for time, it's a total of 19 minutes. What would it be then? We're lucky. We could do 1 minute per square. So again, I'm not going to list each one. Let's go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 16, 17, 18, 19. So now I'm going to graph my points. So we have, at 5 minutes, we have 2 bees. So that's going to be right on the square. Okay, at 7 minutes, we have 5 bees. So here's the 7 line, and I go up to 5, 4, and it's going to be in between 4 and 6. And then at 9 minutes, we have 26 bees. So 9, we're up to 26. So here's my 9 line, 22, 24, 26. So right here. Good. And then I go down at 11 minutes, I go to 20. So at 11 minutes, I go to 20. Good. And then at 13 minutes, I have 21. So that's going to be in between. Good. And then at 15 minutes, I have 14. So here's 15, and I'm right here, 14. Good. And at 17 minutes, I'm at 10. Right there. And at 19 minutes, I'm down to 1, which is almost at 0. There we go. Do I connect the dots? No. Why? Discrete data, because B's are whole numbers, so it doesn't make sense to connect them. Good. Let's do the same thing now for Kayla. Okay. So for Kayla, I don't like my title, but I'm just going to go with it. Kayla's data, let's go make our grid on here. I'll make this bigger to make it easier for me. Always put your grid lines on. Sometimes they're given to you, sometimes they're not. Haven't done this for a while. Okay. This can go. Good. And good. And so count the squares. Again, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 going up. So going up for her, she has the highest temperature of 26. So it'll be 26 degrees Celsius for 17 squares. I go to my calculator to figure out what that number would be. 26 divided by 17 and get 1.52. Again, round to a good number. So I will use, again, 2 degrees Celsius per each square. Okay. Time again, 19 minutes, so we can go 1 minute a square. Don't forget you have to label it. So this will be time, and it will be in hours or minutes. You know, it doesn't say, does it? Every 2 hours during the day, so time here will be in hours. Okay, time should be in hours. And this here will be temperature, and we're going to assume, since we're in Canada, that will be in degrees Celsius. Okay, I should have turned my paper sideways. Shame on me. 0, 1, 2, 3, 4, 5, 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, 2, 4, 6, 8, 30. And I just want to make sure I get this written properly. This will be, what? Nope, get back here, you. Temperature in degrees Celsius. Okay, so let's graph her then. 5 and 12. So 1, 2, 3, 4, 5, and that's 12. Good. Next, we have 7 and 13. So 7 and 13, there we go. Next, we have 9 and 15. So 6, 7, 8, 9, 10. So 9 and 15. Here's 12, 14. So that'll be 15 in the middle. Then where are we at? 11 and 19. So this is 11. That's 19 right below 20. 11, 12, 13, 14, 15. So what's the next one then? 13 is 24. So here's 13, and here's 2, 4. So right there. And what's next? 15 is 26. So here's 15. Then this is 30. So I go back to There's 26. And 17 is 25. So 25 will be right in between. And 19 is 21. So we go up to this line right there. Now, I want to connect the dots, and usually we kind of go smooth curve, connect the dots. Okay, usually we don't just connect them straight forward. We kind of do a smooth curve to show the relationship, to show the trends. You'll be finding more about that out later in science. Okay, there we go. Sketching, interpreting graphs.